opportunity to talk about labs recently. Sorry. This is my topic, and I'm Tan Xinsheng. I'm from Nanjing University. This is the outline of my talk. First, I will introduce the superconducting qubit, which is the main study area of our lab, and then is the analog simulation of we have done. Most of them are topological materials. Finally, is the simulation parity of magnetic effect, which is my topic. Okay, so superconducting qubits are the device based on the Josephson junctions, and according its premise and architectures, there are qubit backbox, fast qubits, and phase qubit. Now the mainstream is called transient. It's a modified cherry qubit coupled to the resonator, and it increases the decrease time. Now it seems as one of the most promising candidates for the future quantum computation. Transient has several advantages, such as coupling strength and the highly tunable parameters. So it provides a very good platform for this quantum simulation. Plenty of good job have been done, such as topological transition on the Haldane model, which is done by UTSB, and the simulation of the time crystal, which is done realized by Georgia University and Institute of Physics CIS. And for the quantum simulation, our lab have our own considerations. Now, we mainly focus on how to realize complex quantum systems with few qubits, such as you use analog simulation to realize the Kerr magnetic fields in well symmetric and the phase transition on the topological maximum model, which is very interesting theory, but not having realized in practice yet. To achieve our goal now, we have to design the new structures, and we use the capital to coupling the qubits with large detuning and large coupling strands. We can design the Hamiltonian that we need. Okay. Now I use measurement of the geometry tensor as a clue to introduce our work. The quantum geometry tensor describes the distance of the quantum states on a primary space. It contains two parts. The first part is the quantum metric, which I will talk later, and the imaginary part is called the barrier curvatures, which is widely studied since it's closely related to the barrier curvature and topological environments. So it plays a key role in quantum computation and condensed matter theory. But in contrast, the quantum metric has lack of experiment, but it's still very important. So that's why we have to start it. In experiment, we use a protocol to measure the metric tensor called Salon quench, in which we rapidly tune the parameters of the Hamiltonian. Then we can extract the metric tensor value from the population of the excited states. Because this protocol has short branch time, so its fidelity is much better than the previous scheme, which has shown here. We have tested the protocol in the direct monopoles, so which is constructing the three-dimensional space. Now, what about the four-dimensional space? A model called the tensor monopole has been predicting the series, but lack of the experiment. It's very interesting. The Hamiltonian is constructing in a four-dimensional space, and its topological environment is described by the metric tensor, not by the barrier curvature. I think that's why it's got the name. Now, first we use we observe the phase transition from the band structures. You can see from here this model changes from the trivial insulator to wide thermometers and the trivial insulator again. Use the sun quench method I mentioned before. We can get the metric tensor values. From here, you can see the experimental data and the theoretical results are in good agreement. In algorithm, we measure the metric tensors. We can get the topological environment of this model. From here, we can characterize the phase transition of this model, and this is the first time we realize this model in a solid quantum system. Okay, now we have measured the metric tensor in 3-dimensional space and 4-dimensional space. So the question is how to promote our protocol in further. For example, how to measure the metric tensor in a non-billion system. Our solution is to prepare a ring-shaped superconducting qubit, and we use parametric modulation to copy this qubit to construct the diamond-shaped Hamiltonian. Realize that, then we can measure the non-billion metric tensors. Also, we apply this approach, the BSA model, which is very important, and we can characterize the topological environment, which is so here. Okay. So our job is basically design the new texture of the superconducting qubits and then map the Hamiltonian into our primary space. The fun part is the simulation of the parity magnetic effect. It's part of the third part of its job is proposed by Dr. Zhu Yanqing from Hong Kong University, and his co-worker, Dr. Professor Blue from Belgium. And its Hamiltonian is constructed in a 4-dimensional space. Each term is like level as gamma is shown here. In the gamma there is a parameter level A. With different A's, this model have different band structures as shown here. Double, quadruple, and triple band structures. Different structures have different topological. as the diamond shape Hamiltonian. Then we use external, a thermal microwave to create the vectors potential. You can see here, if we change the vector potential and the balance structure shifts, and from this location information, we got these fit numbers. The slope of these lines are related to the magnetic field. So we got the virtual magnetic field. And then we want to simulate the change rate of the distance between two different spots. First, we measure the entire balance structure of this model. Since the parameters of microwaves and the modulation pulse are carefully calibrated, so the balance structure are in good agreement with the predicted theory. And if you modulate the parameters, then you can let the degenerate points practical changes as the figure showed. Okay, if you extract this location information, then you can get this distance as a function of the virtual time axis. The left panel is the A equals 0, and the right panel is a situation with A equals 0.5. Okay. The final part is how to measure the second chain numbers. In this case, mass term is added to the original Hamiltonian and open the balance structure. Then we integrate the Bell culture over the entire permanent space to get the second chain number. This theory looks very simple, but actually it's the difficult part in our experiment. Actually, the measuring the second chain number itself is a very important experiment. The simulation of your monopole in the ultra-cold atom has published on Science, and it's a very important verification to the monopole theories. So in our job, we use the similar protocols, which is measure the Bell culture in the linear response to the adiabatic procedures. Actually, it is very. We have to measure the perturbation term in the adiabatic procedures, so it has a very small magnitude. Since we haven't have the instrument such like GPA, so it's very hard for us to measure the accurate the value in the experiment. So we use a game called the STA amplifiers. In the original STA, which is the super adiabatic procedures, we modify the Hamiltonian to cancel the first perturbation term in the adiabatic procedures. In our scheme, we invert this protocol, so we can increase the perturbation terms in the adiabatic procedure, so we can increase the measurement fidelity. So it allows us to get the accurate data without the GPA. First, we tested our protocol on the measuring of the first chain numbers. This is a measured Bell culture, and this is a fast translation data. From here, you can see our experiment data are much better than the previous protocol. Okay. Then we use our scheme on the PME work. The Bell cultures are obtained from the slope of this line. You can see the error bar. is very big. So if we don't use this method, we can't get the accurate calculation. Since this integration is over the entire primary space, so we use a proper truncations in that not in fact our final results. As a predict series, the second chain number is related to the sign of the mass term, not the value of the mass term, and our data has proven that in our experiment, we have measured three value of the chain number. We have measured chain number with three different m. You can see that this second chain number remains the same. Okay. The ideal value is about 0.5, but our experimentation is about 0 to 5. The deviation between the data and the ideal value is mainly because of the decoherence time of our system, and our simulation results can prove that. So here we got the magnetic field and the change rate of the degenerate point and the second chain number. So we can combine them. We got the total current, and we can further study the property of the total current. Here we show in this figure it shows that this total current is linear proportional to the effect magnetic field. Okay. So let's summarize. This is the first experimental report of the quantum simulation of the PME, and we measure the fractional as a spin chain number for the Dirac model. And we think I will work over the probability to explore the more complex topological environments. Okay. These are our collaborators, and these are the members of our SQD lab from Nanjing University. Okay, thank you for your attention. Okay.
Why there is deep variation between this red line also split. So let's imagine the origin red.
You missed one?
Yeah. So the blue on the
this simulation is we simulate the results with the decoherence time. Yeah, this one is the ideal one. We can say that the decoherence time is very long. So to indicate our protocol peaceful. Okay.
Thank you. Thank you. Next session is